Boş bir zaman
Bitti device drivers. Tamam su ya. Bitti device drivers. As we said, buggy drivers cause the system crashes or bad behavior for the operating system. There are some techniques to prevent these. Anyway, we are not going to talk about them. Sometimes, as we said before, sometimes each manufacturer produces its own device driver, but sometimes most operating systems define a standard interface for all block drivers. For example, this and CD-ROMs. Okay, so the same device driver or similar device driver can drive similar devices for block drivers or character drivers, keyboard and mouse. Block drivers. We talked about this. Remember the block drivers. They read and write the data in terms of blocks, 512 byte blocks, or maybe larger or smaller. And you can address the block number. I want this block or this block. So there's a random access. With the character devices, the input output is done by character, and it's a stream. You don't have control over random access. You cannot do the random access. So their device drivers are similar device drivers, or the same device driver for these type of devices, and for these type of devices, the same device driver could be used for some operating system. Okay. So at the top of the, remember we are doing this, hardware, internal patterns, device drivers, and the device independent operations. And then we are going to talk about user level I/O software. Okay. At the top of the device drivers, we have the device independent I/O software. Device independent I/O software. These are the functions of the device independent I/O software. Okay. Uniform interfacing for device drivers. In that part, the code you are writing in that part of the operating system doesn't know the differences between the devices, because the details are isolated from you. There is an abstracting layer. There is a buffering issue. Buffering is important. We had a question actually about the buffering. The way you do the buffering enhances the performance, but sometimes you want speed instead of the performance efficiency. So using different buffering techniques, you can gain efficiency, better CPU utilization, better memory utilization. Sometimes you want faster output. In that case, you might sacrifice some efficiency. Be a little bit inefficient, but be very, very fast. Error reporting. We talked a little bit about it, but we are going to talk about it at this layer too. And allocating and releasing dedicated devices. If you need to use the printer, you need to have access to it. If somebody else using it, somebody else is using it, then you need to wait. And providing a device-independent block size. Remember the block devices, the data is accessed in terms of block addresses. And different devices have different blocks. And it is the task of this layer to provide the device-independent block size to the upper level, user level, so that they can write device-independent code. Okay? Uniform interfacing for the device drivers. Okay? If the operating system has this kind of a structure, these are the device drivers: SCSI driver, USB disk driver, SATA disk driver. Okay? If they have this kind of structure, then obviously you need to write different code to interface with the different device drivers. But if the interfaces are standardized, then writing code for different block devices might be easier. So with a standard device driver, okay, this picture, This is what we prefer. Okay. For each class of device, such as disks or printers, the operating system defines a set of functions that the driver must supply. Okay, you are saying that if you are writing a driver for my operating system, and if you are a printer, then you need to implement these functions. What are those functions? Print a character, line feed, page feed, reverse the page, and etc. That kind of stuff. So you define these kind of functions. It's like a interface design, Java interface design. You design this interface, then you ask the device driver to write those functions, to implement those functions, and then operating system simply call those functions using the device interface. Okay, so this is uniform interfacing. Often the driver holds the table with pointers and stuff for these functions. The driver has a table like the polymorphic function tables. Okay, the driver holds a table with the pointers, and the operating system follows those pointers and calls those functions. Okay, in Unix, major device number for a device are there is a major device number and a minor device number issue concept in Unix. Major device number shows the type of the device, if it's a disk device or the printer or the mouse and that kind of stuff. Minor device number shows the which one of that, because you might have more than one hard disk on your system or more than one mouse on your disk, and these numbers are written are kept inside these device files. Under the their directory, you have these files. You keep this information in the inodes for those files. Okay, so this is uniform interfacing. We don't prefer this, but we prefer that. So for these type of interfaces, operating system says that you need to define this function, and this function. Once you have these three functions, it doesn't matter if it's a USB driver or a SCSI disk driver or another disk driver. And another issue with the buffering, there are different ways of doing the buffering depending on the okay, I don't have that picture. Depending on your situation, one of them might be suitable for you. The first one is here. Let's say we have our DSL modem communicating with the user space. If I am reading the bytes one by one from this modem to the user space, then I am using this picture, a unbuffered input. Okay, unbuffered input. What does that mean, unbuffered input? I am not buffering anything. I am using characters or the data one by one without doing any buffering. So of course this has problems. Why this has problems? Because if I am receiving this data, okay, if I am receiving this data from a DSL source, and this is my user space, if some other process is running other than my process, then since the data is not buffered, I might lose some of the data because I am not buffering anything. Buffering is good for not losing any data. Okay, so for that case, let's say let's put the data inside the buffer in the user space. In the user space, I mean, this prevents a number of problems buffering it in the user space, but since still I am in the user space, I don't have to control most of the time. This still has some problems. What are the problems? Problems are usually when I do this, when the modem is writing to this buffer, and let's say these are the pages in my memory, and due to page replacement requirement, my pages are replaced. So when does the modem is going to write, it becomes a problem, because user pages are very likely to be replaced if there is no enough memory. That's why they invented this picture. They say that we should have a buffer in the kernel space, okay? The modem should write the data to the kernel space, and when the buffer is full, then we can copy the content to the then we can copy the content to the user space. And since the kernel space pages are pinned, they are not replaced. Okay, they are pinned and they are not replaced. Then that means that this is much safer place to write your data. That's a good solution. But in that case, I need to keep the buffer 2 times. Okay, one buffer here and another buffer is there. One problem might be this. Okay, this one is full. Okay, while I am copying data from this buffer to the other buffer, I continue reading from this modem. That might create a problem because I am busy copying from this buffer to that buffer. That's why they created this model about double buffering. Okay, when this buffer is full, while you are copying this to the user space, the modem keeps writing to this second buffer, double buffer. Okay, when this one is full, this one is copied, this one is takes the data from the modem. So these are some buffering scenarios. Each one has a different purpose. This one is almost never used. This one is dangerous. This one and this one are the more popular buffering mechanisms. Okay, any questions? Any questions about the buffering? So without the buffering, I cannot keep up with the data from my I/O devices because I/O devices are slow, but they give me the data at a very regular intervals. And if I don't have any buffers, since my processes are blocked most of the time, I might lose some of the data that I receive from the I/O device. Buffering is required. Sometimes instead of using this double buffering, we have the circular buffer. What is circular buffer? It is like that. Okay, it's an array. This is the beginning and this is the end. This is the beginning and this is the end. When you move this pointer from here, there and there and there, and this one, it can move forward too. When this one runs out of space, then this one goes back to at the beginning. Okay, so this is called a circular buffer. And for this case, so in the circular buffer, hardware advances the first pointer. So the first pointer is advanced by the hardware, okay, from the I/O device, and the operating system advances the second pointer because it removes the data from the end. So one is advancing the first pointer forward, the other one is advancing the second pointer. So this is used in many cases. For example, in the consumer-producer problem, producer-consumer problem, we have the same structure most of the time. Because I/O device is something like a producer, right? It produces data and you consume it. And buffering is a problem with I/O devices actually. Okay, any questions? Circular buffers are alternative to double buffers. Another situation here is many layers of buffering. Okay, this is one case. In my user space, I have a packet. I want to send it to my client on a different position on the network. I have my buffer. I copy the contents of this buffer from the user space to the kernel space. From kernel space, the buffer is copied into the buffers of the device controller. Okay, device controller, and then these data is sent bit by bit to the other device controller. It is copied from this position to that position, and again to the user space. So I have 1, 2, 3, 4, 5, 6 copies of the same data over the network. which is inefficiency. Okay, sometimes we involve many copies of a packet buffer, but the positive size of buffering is much more than problems of this kind of buffer copy. Okay, so we need to be careful about these kind of situations. Again, remember we were talking about this device-independent I/O software. We talked about uniform interfacing, buffering, and error reporting, and we are going to talk about error reporting and these two. Okay. Errors, device allocation, and block size. So these are some of the issues with the device-independent I/O software. Many types of errors. There are user errors. What is a user error? Let's say user error might be you are trying to create a file on a CD-ROM. Okay, this is a user error. Okay, this error can be caught at the higher levels of the operating system because operating system knows that some of the devices cannot create new files. Sometimes there are I/O errors, bad sectors. On the desk, I have a bad sector, and I cannot write or read from those sectors. These are lower level errors, or errors that cause system crashes. For example, there is a bad sector at the system hard disk root. Okay, there is a bad sector, and all the data is lost. You cannot do anything, so it causes the system crash. So the errors might range from user errors to the system crashes, and each one has to be dealt differently. There is no standard way of doing it. Device allocation, I talked about it. Printers cannot be shared; they need to be allocated to different processes. And the block size, normalizing the block size. Different disks may have different sector sizes. It is up to the device-independent software to hide this fact. Okay, because the user-level software, user-level programs, they don't want to know about the sizes of the blocks for different devices, because otherwise I need to change my program. I need to write a different program for different type of hard disks. That's not good. So somebody has to do this abstraction for me, and it's the task of the device-independent software layer to hide this fact from the users. So these are the things that we are going to talk about. The device-independent software layer. Then on top of this device-independent software layer, we have the user space I/O software. Okay. So these are the programs that we write, C programs. When you write a C program, open a file, okay, on the desk, write like 10 lines of text to the file, then close the file. Okay, 3 statements. I am making 3 system calls in this case. Opening a file, okay, writing to an I/O device, and closing a file. Okay, 3 system calls. These are all user process commands. My C program stdio library takes my system of C functions. For each function call, they make a system call. Okay, these system calls might be sometimes very trivial, very easy. For example, this function open. When you open a file, it can create a file. It can open an existing file. It can open a file for appending. When I make a function call open, C function call, that C function call doesn't do much. It just calls the operating system routine because it needs all the data. It has all the data that it needs, and it sends that data to the operating system. But sometimes the situation is not that easy. Sometimes I do this. Printf percent 1.2. I couldn't write it. Percent 0.2 F and F. Okay, so I need to do some kind of a formatting, and the operating system doesn't know about the formatting. It doesn't care about the formats of your string. So printf has to do lots of formatting work before sending the string to the operating system. So the I/O formatting is done at the user level. Okay. I am, as a programmer, C programmer, I am not doing it, but my C library does it. Okay. After the C library does this, it makes a system call saying that I am gonna send this string to this I/O device. Okay. So it takes that I/O device, and this device independent software, it handles the naming. Okay, which device, because I don't care which device I am writing at this place. It talks about the protection. Can I create a file on the CD-ROM or not? Or can I write to somebody else's file? Okay. Block sizes and the buffering and the allocation. Can I write to the printer at this time if I'm trying to send something to it? Okay. Then the device drivers. Okay, this information is going that way. Okay, set up device registers, check the status and etc. These are talking that way. Then I have the interrupt handles, wake up the driver when the I/O is completed. And hardware does the I/O operation itself actually, using the device controller. And the information goes back that way. So for the user processes, that's what we have been doing actually when we write programs for the C programs or C++ programs, Java programs, whatever. We have been using operating system routines. Actually, we are calling functions that those functions are calling the operating system routines. Okay, so at the user space I/O software, there is this small thing, spooling. I'd like to talk about this a little bit. Spooling. Spooling is usually used for printers. Okay, there is a spooler directory